Hello, this is Connie Smith. This is a short presentation on my 2020 paper for the International Conference on Performance Engineering on software performance anti-patterns for cyber-physical systems. This is a short presentation. It will focus on the three new software performance anti-patterns that we have found common in cyber-physical systems. I'll refer you to the paper for other details, the related work, the 6 previously defined software performance anti-patterns that we have found common in cyber-physical systems. People tend to learn more from examples of what not to do, especially when it comes to performance. So these performance anti-patterns provide guidance and insight into typical problems to look for. They define the problem and the solution. Note that these anti-patterns may apply to other types of systems, and other anti-patterns may apply to CPS. The set here we have found to be the most common. Poor performance of cyber-physical systems is noticeable, annoying, and may even be dangerous. Some examples of poor performance include low throughput that may not keep pace with the arrival and processing of new information, jitter such as flickering of displays, pixelation, irregular responses, pauses while the system catches up, and so on. Lack of response to user input because the system is busy with the previous request. Timeouts, error messages. The startup time is often problematic. For example, we find these screens and others annoying. Embedded systems then and now. I'd like to refer you to the paper for some of the reasons why we find more performance problems in today's cyber-physical systems. What I'd like to talk about is an example I learned about a few years ago at the Embedded Systems Conference. A particular manufacturer introduced a feature for users to be able to program a washing machine to run later for cheaper electricity. And upon implementation, they discovered that the display would periodically flicker, and they started trying to figure out why. First thing they claimed was that profiling didn't work. Now that's a whole other story. But after trying various things and being unable to resolve the problem, they hired some consultants, and the first thing they did was to write a custom activity monitor. They discovered that the washer had 2 processors, and both were approximately 100% busy. The software was written in Java and running on Windows Embedded OS. They suspected that the culprit was a process called GC069788 because it was always running during the flickering. Turned out it was garbage collection. A process was waking up to see if it was time to start the washer and then sleeping and leaving garbage around when it did it. There was a very short sleep interval. It woke up once per second. So the performance improvement focused on tuning the garbage collection, and they managed to stop the flicker that way. But think about this for a second. Is that the real problem? They had 2 processors that were 100% busy to save electricity, and the display was lit all of that time? Really? So that takes us to the first of the software performance engineering anti-patterns for cyber-physical systems. Are we there yet? We've all heard this phrase too many times. In cyber-physical systems, it's often due to polling, as in the washer example. You also find it when logging, during or after the completion of things like commands, events, status, information for audit trails, and so forth. The problem occurs when there's high overhead for polling and the interval's too short. For example, polling once per second for the washer when it's not due to start for hours. Solutions for Are We There Yet? If you have the luxury, you could select a platform that's appropriate for the task. For example, an interrupt-driven operating system can wake up the process when it's time. There's no polling necessary. If you have a system with a notification feature, be careful. It may actually be implemented with an internal polling loop to see if it's time to send the notification. Determining the proper frequency and timeout usually requires analysis and experimentation. For the logging, the application characteristics can indicate the best points in time to record the information. And if it's possible, you might want to process the logging asynchronously so it doesn't add to the user response time. The second CPS antipattern, is everything okay, refers to processes that check the status of the platform and/or the system state and issues warnings of problems. It's a problem when there is significant overhead to dispatch the processes doing the check. And also note that the platform checks themselves may deplete the resource, and warnings that occur at inappropriate times affect usability. This example shown in the table was found in a very large startup scenario, one of many significant performance problems. These three are a subset of the total checks that ran as system tasks, quote, in the background, but there was only one processor, so they impacted the response time. These ran every 500 milliseconds, so there were 445 checks of battery life, disk space, and updating the status during the startup scenario. All of the checks together consumed about 20% of the startup time. The solution for is everything okay is first of all to design the solution. Don't just use default system processes that check status. The solution may be event triggered, where you use an interrupt or notification that it's time to issue a warning. May be time-based, where you use intervals that are appropriate for the resource depletion rate. It may be event-based, where it's done at key points in the scenario, or it may be state-based, where the frequency is tailored to the availability of the resource. In this example, an event-based solution would be best, where we check the platform status once during startup. There may be other checks during the operation, but we're addressing the startup scenario at this point. The third CPS antipattern, where was I, happens when a process does not remember state information, so it always starts over, or when state is automatically restored, but is frequently not the one that you want. One example happens in an avionics application that reports weather predictions. So for example, if I'm interested in winds aloft at various altitudes, and I happen to be flying between Denver and Santa Fe and deciding which mountain pass I would prefer to fly over, if I boot up the application, after a very long delay, I get a message saying there's no network, when I would prefer to see the last results that I viewed. Another example is another avionics application where I would like to change one parameter of an instrument approach procedure, but the avionics requires specifying everything. So that's very frustrating and distracting and urgent when I'm flying in the middle of clouds and need to do this quickly. The solution for where was I is to first check for connectivity and then either refresh or display the most recent results. We need to design for the most critical and/or most frequent situations, and to do that we need a requirement specification for frequent usage and failure modes. Things like likely settings changes, lack of network connectivity, and actions to take then, and device configuration changes. Now these are examples of usability, but that affects the end-to-end user performance, so it's actually more important than just device performance. Here's another example of a cyber-physical system with performance problems. You may be able to see at the top of the stairway in the green circle is a spa, which is an excellent thing to do on a cold winter night. However, this scenario happened far too often. I would climb up that hill, 12 steps, 6 inches of snow, icy path, 18 degrees outside, open the thing up only to find out that the water was too cold. So the last time I replaced the spa, I selected one that had a device and an app that would let me control the temperature remotely. So this example shows the effects of all of these performance antipatterns. First of all, the app always starts from the beginning, even if you just used it. So that's an example of where was I. And it always does this platform check. Is everything okay? It's checking for network connectivity. Now this is going to go a while. I just want you to see the effect. So it fails after an overly long timeout. It's about almost 60 seconds. So that's an example of are we there yet? Notice that it remembers the name of the spa and it remembers that it was connected, but it times out and starts over. So it's getting ready to tell me now that I have to go back and check my network connection. Even though it had it visible before, now it's saying that it's not. So this is going to change the network connections and try it again. And it's going to fail a few more times, and eventually it never does work in this example. So that example shows how frustrating these performance antipatterns manifest themselves in actual systems. As far as I know, that system is no longer available. I think that the app failed so miserably that the whole system was abandoned. It no longer works. Now that concludes the section on the new software performance antipatterns. These are the previously defined antipatterns that we have found prevalent in cyber-physical systems. I'll refer you to the paper for more information on these antipatterns. I'd like to leave you today with a few observations on this collection of software performance antipatterns for cyber-physical systems. First, we believe that by a domain-focused collection of likely antipatterns, such as those for cyber-physical systems, helps with the detection and the correction of software performance antipatterns. Second, we always use a design-focused approach to correcting performance problems. And we recommend that if you're using a measurement-based approach, that you correlate those measurements back to the design. Otherwise, everything can look like an extensive processing problem, and it doesn't explain why you have the extensive processing. Third, end-to-end performance matters, and so does performability, which is a combination of reliability and availability. Failing to do so may even lead to product failures, as in the spa example that I showed you. And lastly, bad smells are potential performance problems. And we believe that guilty performance antipatterns are a far better method to use to detect and correct performance problems. And that's demonstrated by the washer example. The developers spent a long time chasing bad smells without actually finding the real problem. And by using antipatterns, it leads you to the bigger picture that it's not just garbage collection. There are bigger problems with the design itself. Thank you for your attention today. If you have questions, we'll be answering those in the Zoom session on Friday. And there's a link to the paper if you don't have it, and other information is in the Performance Solutions book. Thank you very much.